Hi, this is a presentation I'll be making to the Retired-Technophiles-of-the-Main-Line Meetup group. Really just walking through it to find out what my timings are, get an idea how long it's actually going to take to get through all the slides and what I should and shouldn't include. So here we go, we'll see what it's like. So first, just some background on ESP32s. So they're a microcontroller, so basically a microprocessor on a chip. So first we'll have a look at the ESP32 and then look at some of the ways the ESP32 gets configured. Later on, I'll start looking at the software that you run on ESP32s, how you normally run things using an ESP32, and then I'll look at how I actually used ESP32 for a project I was working on. So first, looking at the basic ESP32 chip. It's produced by Expressive company, and just going through some of the highlights here. I actually highlighted it on the slide. So it's a dual core processor, so two 32-bit microprocessors on the one chip, and that's really useful for when you're dealing with network connected devices. You can have some of the network activities and some of the interrupts and things that get associated with network activities running on one processor, and let the other processor run your main application program. So useful to have the two processors on the chip, and some of that's taken care of by the software on the chip. You don't even need to get involved in saying which processors go to which processor on the chips. And they're pretty speedy chips, like I said. They're 32-bit, running at 160 or 240 megahertz. So a fair bit of power there for a little microprocessor. As well, there's one more processor on the chip, which is called the ultra low power processor. It's really to run the chip in low powered state. So really puts everything to sleep except for this low power processor that uses very little power. So you could run the device on a battery, and then you can set up this low power processor to wake up the rest of it when certain things happen, say an interrupt on one of the IOs or something like that, or a timer. So you could have your whole microprocessor, micro device sleeping most of the time, maybe wake up every 5 minutes to get some reading, maybe get the temperature, something like that, and then go back to sleep, and it can last quite long on a battery that way. Has a decent amount of memory in it. If you've looked at some of the chips associated with Arduinos, this is quite a lot. So 520 kilobytes of SRAM, which is a lot of RAM to play around with, and usually 4 megabytes of flash gets configured. So flash is kind of the non-volatile memory where you can put your programs that you're going to want to maintain between power cycles and configuration parameters, those sort of things. As well, the ESP32, one of the important things it has is built-in Wi-Fi. Note it's B, G, or N, so only single band, and it's set up for 2.4 gigahertz Wi-Fi. As well as Bluetooth support on it as well. I haven't used the Bluetooth, but you can also set up Bluetooth services on it. So that's useful. Sometimes you want to be able to control your microprocessor from, say, a cell phone. So having Bluetooth on the device makes it easier to get that sort of functionality working. There's a bunch of peripheral interfaces on here. Again, I haven't used many of these. So 18 channels of 12-bit ADC, analog to digital converters, 2 8-bit DACs, so digital to analog converters, 10 touch sensors, so it makes it easy to set up kind of easy to use or easy to configure buttons by just wiring to something that you can touch. So you can have up to 10 of those being natively supported. An SPI interface, I2S interface, I2C interface. So you'll find a lot of microprocessor add-on hardware uses these different types of interfaces. 3 UARTs, SD, SDIO, MCC, EMCC host controllers, SDIO, SPI, slave controllers. I don't think I've ever used those, so one more thing it has. So it's, again, the highlighted thing here that was useful to me for using in my project where I want to be able to interface to the network, do network monitoring, so having the ability to have a Ethernet connection as well as Wi-Fi connections is important. So that's built in natively to the hardware as well. Ethernet MAC interface, and you can. I'll show you the development board that I actually used that implements that. CAN bus 2. Some of these things I've never heard of, but they're probably important to people who are setting up microprocessors. Infrared remote control. So if you want to be able to control the microprocessor through an infrared remote control, the basic hardware's built in. Motor pulse width modulation. So if you're doing robotics, being able to do PWM to motors allows you to control stepper motors, things like that. LED pulse width modulation. So again, being able to connect up LEDs, but as well being able to control the brightness of those LEDs using PWM. It's got a built-in Hall effect sensor, ultra low power analog preamplifier. In addition, there's some good security features. Again, I didn't use these explicitly, but I did make use of them. So things like when I did probes on HTTPS and SSL connections under the hood, I think it's using the built-in RSA and cryptographic hardware acceleration to enable that. But this is built in so that you can add services to the ESP32, probably the WROM modules. So you can have things like certificates associated with a device, so you can check that only your devices are the ones connecting, those sort of things. And power management, we can see there it shows you the support for the deep sleep current, so 5 microamps when it's in deep sleep using that low power processor is pretty low, so should get a lot of life out of a battery connected and managing the device. And then you see wake-ups from GPIO interrupts, ADC measurements, competitive touch sensor interrupts. So all things that can trigger the ultra-low power processor to start up the main processors again. Now have a look at moving from the actual ESP32 chip through the ESP32 standard modules and their use on development boards. So a little, again, some background here. We see on the left-hand side here, the actual ESP32 chip is something you don't usually just buy by itself. You usually get it as part of a ESPW ROM module, which is packaged up by ExpressF. So you see an example of it here, this little metal canister. So inside that is the actual ESP32 chip, but as well inside that module it usually contains things like flash memory, additional discrete components for things like doing AD, and then a little antenna for the wireless Wi-Fi connectivity and Bluetooth connectivity. So again, you don't usually deal with the actual chip, you do deal with the chip as part of this WROOM canister. Moving across here, usually what you'll do is, well, I've been buying the ESP32s on a development board, and you can get different varieties of this. So this is where you can go out and get a particular development board that has this ESP32 WROM module on it, but has some additional hardware on it depending on how you're going to use the ESP32. Okay, so this should give you an idea of what a development board typically looks like. Here I've got it mounted on some breadboard. That gives you an idea of the size of it. Has some pins in this one. You don't necessarily have to get these with the pins installed. Has a serial connector, an LED, some buttons on it. So getting back to the slides, so this is our development board, and then one more level of abstraction after that is you can get various development boards. So like I said, you can get development boards that support doing different things. So get an idea here on, this is just a listing out of Amazon where I put an ESP32, so you can get boards like I'm using. You also get boards that have built-on displays, and another board I use is one from Olimex, which has the built-in Ethernet connector. Typically when you get these boards, you're also going to get a high-level schematic like this. So this is for my high let go board, so it shows you all the pins out, where the buttons are, what they connect to, where the LEDs are, what they connect to, how the power is set up. So typically the development boards will take 5-volt power, but drop it down to 3.3 volts for use by the ESP32 module. And you'll see again the Olimex board I use also had a schematic that shows how the Ethernet connection was connected up. And I included in here a bunch of URLs. So for example, you can get ESP32s from Amazon. So here's an example of different ones you can get. You can see there's millions of them. Good place to get them, Alibaba. Website has millions of ESP32s. Sometimes you can find some weird ones out here. You know, even get something like this. So this is an example of a ESP32 or watch using an ESP32, which could be neat. I'm going to try and get one of these sometime if I can get hold of it. But do this sort of neat thing where you have a fairly technical interface on the watch. I don't know whether I could even read that, so small. But just showing you there's a lot of different hardware out there available. Also be aware, out on the Expressive site there's a lot of good information about the WROM module, so very detailed data sheets about what they have on them, how they're configured. So a lot of good technical information there, as well as a lot of good usage and using the ESP32 for different software scenarios. There's a lot of information on the Expressive site for that as well. And just looking at the development boards that I use, so again, for this video I'm going to show where I'm using a HighLego board, so just a basic development board. These are typically $5 to $10 depending on whether you buy them off somewhere like eBay or Amazon. Tend to be a bit more expensive on Amazon. But a good basic development board, and then the one that I ended up using a lot is this Olimex ESP32 gateway. Like I said, it's got a couple of extras on it for hardware. It's got the actual hardware Ethernet connection, so because I was doing network monitoring with mine, using a hardware connection worked out better than using the built-in Wi-Fi, and also has a dedicated micro SD card reader. Okay, just finishing off the basics. So how do you use the ESP32? So on the software side, you can use it like Arduino, and I actually started off, I used the Arduino IDE, and you can still write Arduino C, C++ sketches, and I got as far as using the Arduino IDE to get the LEDs blinking, and did some Wi-Fi pings. So someone who's used to C, C++ and using the IDE, this may be the way to go. However, I prefer to use something like MicroPython, or a higher level language where it has built-in garbage collection and a bit more support for software development than at least I get from C or C++. So I'm going to go through, so the second half of this presentation is going to be about how I actually used it, but some of the other choices as far as software, so you've still got the basic Arduino type C, C++ type programming, but you can also do things like use JavaScript. There's interpreters you can load up on the ESP32 for that. You can use CircuitPython, which is a variation on MicroPython that Adafruit produced. So it's actually always based on MicroPython, but they have some nice support and ease of use things in their version of MicroPython called CircuitPython and their IDE. But I didn't actually use that. It's only if you're using Adafruit hardware. And you can also do things like run RTOS on the ESP32. There's a Ruby interpreter and much more, as I say there. One thing to be aware of, again, out on the Expressive site, and I've put the link in here, there's the API reference, really the C, C++ API reference. And so we can see here there's a very rich API for using the various functionality that's built in the ESP32. So you can sort of do a deep dive through this to see how you use some of these capabilities. And if you're using some of these capabilities, this may be a reason for using C, C++, because again, the APIs in that, not all the APIs have been ported over to things like MicroPython. Most of them are, but not all of them. So then you've got the choice of either using C++, C++ to do your programming in, if you want to use some of these unique APIs, or you can build a wrapper around them in MicroPython, which a lot of these have been wrapped already, to use in other languages. So this is a good place for a natural break. Second part of this, I'll be more hands-on, just show you how I actually used ESP32 in my project, and show you things like how you flash ESP32, how you get software on it, and some examples of MicroPython code. So the second part of this looks at how I'm actually used the ESP32. So I used it on a project called ourProbes. So this is something I've been wanting to put together. So basically create a network monitor where remote probes can check on network bandwidth and latency, and do checks on, say, web sites to see what the time to first byte is. So all things where it checks, how network endpoints respond over the network to that particular location. So those remote locations, I wanted to use low-cost devices to do these network probes. So you can see in this diagram where I decided to use ESP32s as the endpoints. They do the network capability tests. So like I said, they do pings or bandwidth tests or time to first byte tests. And all that information is being communicated to Google Cloud Platform, where I'm using Cloud IoT Core to receive MQTT information from the ESP32s. And then that goes through, and the resulting data goes into a Firebase database, again in the Google Cloud Platform. And I wrote an Angular front end to actually look at that data. So this gives you an idea what the ourProbes Angular application looks like when after you've signed in. And if I go into the overview page, it shows you what is shown on that presentation, where for all the different devices, so D1, D2, D3, D4, and so on. So those are the remote probes, the ESP32s, reporting on how these different what I call probes, network probes, are behaving. But as well, we can look at the actual trend data. So by default, this one looks again at that New Zealand Debian site over the last 7 days, and this is data that's been collected from those ESP 32 endpoints, consolidated, summarized, and then graphed. So getting back to the ESP32 specific part of this project, what I wanted to do, and it took me a little while to work it out, is work out what programming and tooling environment I'd use. In the end, I decided I'd use MicroPython as the language that I'd use on the ESP32. I prefer it to something like C because it's just kind of a little higher level language. Also, I was already using VSCode for keeping all my code, and I was putting all that code in GitHub repositories. So I still wanted to maintain using that development environment of using VSCode and GitHub, and actually integrate the ESP32 specific code into the rest of my project for ourProbes, which had a lot of JavaScript code, Angular code in it. So just showing why I use GitHub. So this is my GitHub repository for ourProbes. So again, this is integrated with the VSCode IDE, and all the folders that I have down there synchronized up to GitHub. So it allows me to do all the good source control things, as well as being able to move from one machine to another and easily resync based on my centralized GitHub repository. So it has things like folder for all the source code. In here I have two folders, one for MicroPython device. So there's all my MicroPython code that goes out to the ESP32. And another advantage of using Python was I could do another version of the device just using plain Python, using a lot of the code that I created for the MicroPython, and put it in this Python device. So the way I did that was use VS Code as the IDE for the whole thing, which meant I needed a way of getting the MicroPython code onto the ESP32, and that's where I used this add-on, VS Code add-on called PyMakr, which integrates, or you can set up a integration point where certain parts of the source code in your project can be sent over to the ESP32, which is, and also allows you to do things like run that code on the ESP32. So that's what I set up. So what I'm going to walk through, I'll just show you how I do this. So the first thing you need to do is be able to flash the firmware onto the ESP32. If you're using the Arduino IDE and C, C++, then you're going to be flashing the whole program every time you make changes to the program to the ESP32. So you're going to follow some of the same process of using something like the espTool to flash to the flash memory of the ESP32. Because I'm using MicroPython, I only needed to flash the MicroPython once to the ESP32, and then after that I can just send the actual code to the ESP32 without having to reflash the whole thing every time. At the moment, only the MicroPython core code is held in flash memory on the ESP32. There are some options where you can also put your own code in there, but I didn't go that far. I didn't really need to. There was enough room in the SRAM on the ESP32 to keep the application-specific ourProbes code just in the SRAM without having to also integrate it into the code that gets flashed to the main flash memory. So let's have a look at this. So first I'm going to have a look at how I flash MicroPython to ESP32, and I'm going to use the ESP32 tool. So I'm going to bring up a DOS window to do this from Windows. Okay, so I'm going to follow the instructions for getting MicroPython onto the ESP32 board. The links in that presentation, basically go into micropython.org, download ESP32, and I'm going to go through these steps. I'm going to run the espTool, which is a Python program. So if you haven't got Python installed on your PC already, you need to install Python version 3 on it, and there's some instructions here for how to do that. So I run the espTool first to erase the flash memory, and then I run ESP32 tool to write the image of MicroPython onto the device. And the image I'm going to use is this one here. It's a little, well, this one here. It's a little old, but it's the one I show on in the presentation, so that's the one I'm going to use. So I've already downloaded that down to my downloads folder. So let's try this out. So first thing, you see I've already done it here, but if you do a mode when you're in Windows, it shows you what devices you've got connected to serially, and it shows I've got a device on COM3. It looks a lot like my ESP32 board. So I think COM3 is where the device is. So the first thing I'm going to do is just erase that device on COM3. So the erase is pretty fast. You see here it connected to COM3, ran the erase flash command, and we're done. And the second part of the installation process is to get to write that bin file I downloaded of MicroPython into the flash memory. So I'm going to copy this command. Basically it's saying run espTool. It's going to be for ESP32. I'm using COM port 3. I put in the baud rate there just because if you force it you can get a faster download. Command is I'm going to write the flash. I'm going to start from hex 1000 address starting point, and then this is the location that I downloaded the MicroPython code bin file to. So let's try that out. And the process, if you're using a Mac, the process is almost the same. Slight variations on how you name COM ports on the Mac. But that web page explains the differences anyway. So once this is finished, I'll have installed MicroPython on my ESP32 device, and after that I can just talk to the ESP32 device to do MicroPython things and load up code and stuff. So let's do that. I can close my DOS window. I don't need these instructions anymore. And I'm going to bring up my development environment. So Visual Studio Code. I'm going to open up the sample code. And as I said, I'm using Piemaker, so it's already installed as an add-in in this project. So the thing I'm going to do is connect to it. So one thing you need to do with Piemaker is in these all commands, it's got project settings. I've already set this up to set the address to COM3, but if you're using Piemaker for the first time, you got to know the COM port that your ESP32 is on and adjust it here. There's other settings in this Piemaker config as well, things like what files to ignore and where the files are that represent the project to go down to the ESP32 device. So that looks correct to me, so I'm going to click on this to make the connection, and you see it's connected to COM port 3, and I'm getting the three greater than signs, so that means that I'm connected to COM 3 and I'm talking to MicroPython using the REPL interface, which means I can do things like I can do MicroPython stuff to it. I can also load up libraries. So now that's there, let's have a look at how I'm using Piemaker and VSCode to do this. So let me actually increase the size of the screen a little bit as well. So I have MicroPython installed on the ESP32. I've got my VSCode development environment up and communicating through Piemaker to that ESP32. Okay, so let's have a look at some examples of MicroPython code running on ESP32. And this is what I'm planning on going through. So I've already flashed the ESP32 with the espTool. We've connected through the Piemaker via the serial connection and seen the REPL command line prompt come up. Just show you one thing here. If you don't want to use VS Code, but you still want to use MicroPython, another way to there's a few different ways to have a development environment talking to an ESP32, but the other main way is to use rshell. And just to give an example of what rshell is. So we're in a command window. So after you've installed rshell, you can just use the Python pip utility to do that. Then you can do a rshell -p for port. And in my case, my device is on COM3. And you see it's connected in. Important thing here is evaluation board name. It gave the name of PyBoard. I'm going to change directory over to PyBoard, so my file system commands are relative to the PyBoard directory. So I do it cd over to PyBoard. Now I can do things like ls, and I can see what files are present on my ESP32. You can do all sorts of things. You can do rsyncs, you can do file copies. So again, if you're using this in combination with an IDE, you can have some batch files set up or commands set up to use rshell to get your files to and from the MicroPython running on ESP32. Okay, now let's have a look at using VS Code to use MicroPython and Piemaker to work with the ESP32. So I'm going to first show the Blinky PI example, which is kind of the hello world of the microcontroller world. So I'm going to bring up my VS Code environment. Again, all this is up in a GitHub repository, and we're going to have a look at the Blinky PI MicroPython code. So just walking through the code here. So import time, because we're going to use time to do some sleeps. I'm going to import from machine, which is the definition of an ESP32 for MicroPython. So it does things like importing pins. So I can identify IO pins this way using the pin library. And now I've set up a variable called LED, and the definition for LED is pin 2, where it's set as a pin out. So on ESP32, the generalized IO lines can be set as either input or output lines, and so in this case I've set IO line 2 to be a output line, and that's connected to the LED. If you remember from the schematic earlier, LED was set up on GIO 2. And then we get into the actual code. So this is MicroPython code, and it should look exactly the same as what Python code looks like. Okay, so for x in range of 5, so steps through 1 to 5 basically, and each time it sets the LED value. So our LED was set there, so it's setting output GIO 2 to true, which turns on the LED. I print that it's turned on. Then I use the time library to sleep for half a second. Then I turn the LED off, set the value to 0, sleep for half a second, and print that it's off. And let me just bring up my board while I do this. And the nice thing about Piemaker is it has utilities in it to make running this code easier. So first I'm going to I need to go over and disconnect my rshell, and now I should be able to connect through the console here. And what I'm going to do, if I right click on my code, one of the Piemaker utilities is just to run the current file, which makes it really easy getting the code over and onto the device. So I'm going to run it, and we should see the LED blink on and off 5 times. So that's kind of one really easy example of code. Another piece of code I wanted to show was one of the big things about the ESP32 has built-in networking and Wi-Fi. So this is just an example of the MicroPython code to get you connected to a Wi-Fi endpoint. So in this case, I'm importing utime, which is just the MicroPython version of the time library. It's actually synonymous, so you can use U in front of the standard Python libraries to indicate that it's a MicroPython library, or just leave it as the MicroPython library name, like time. It's still going to be the MicroPython version of it that it uses. And I'm going to import network. So if you go out to the MicroPython website, you'll see all these APIs and what libraries are available, and one of them is for networking. And just going through the code here, I just display that I'm setting up the network. I'm setting up a station, and the type of network is wireless LAN, and it's going to be a network station. I just set a timeout value, so connection can take up to, in this case, 10,000 milliseconds or 10 seconds. And then in this loop, while the station isn't connected, so we've made the station here, and we're going to perform this until it's connected. So we're going to connect to the network. So we're going to make that station active, but doesn't mean it's connected yet. It's just an active station instance. And then we're going to connect with the SSID and the password for my guest network. And then while it's getting connected, it's going to stay in this loop. So while it's not connected and the connection milliseconds is still greater than 0, it's going to keep going around in this loop. So it's going to print that it's waiting for the connection, number of milliseconds left in my connection timeout. It's going to decrease the connection timeout by half a second and go to sleep, and then come back around again and check whether the connection's connected. when it drops out of that loop, it'll display the network config information. So same thing here. I'll just use right click and run the current file, and you'll see down here it's connecting, and we got the connection after about 4 seconds, and you can see the network config information and the IP address that was assigned. So once you've got this station IF network connection set up, there's other libraries, including the network library, where you can do things like gets out to websites, all sorts of network things. And you'll see in my let's go there now, in my ourProbes project, if I go into the MicroPython device folder, so this is all the code that I use for my ourProbes ESP32 devices. But you see it's running through here, and one of the things here has a piece of code that looks suspiciously like that Wi-Fi, getting that Wi-Fi connection. And then it runs through, does all the different code for running different probes to test different network conditions out there. So it's still very much like that the example of Wi-Fi connects, but a whole bunch more stuff in here, including libraries for MQTT. And there's a lot of libraries out in the world for either MicroPython, and if you can't find the library that you need in MicroPython, a lot of times you can just get the Python version of the library, make some modifications to make it run in MicroPython, and it usually all works. One thing I did run into quite a few times was run out of memory, or because there's garbage collections that need to happen to free up memory and have continuous memory on the device because there's not a lot of memory. I was doing a lot of GC connects. Again, it wasn't too onerous, especially the way I've set this up. So if worse comes to worse, in the case of how I'm using this, the device, I just rebooted if it actually it's pretty much falling apart and hasn't got enough memory for anything. I get it to do a self reboot. It restarts and then reconnects and gets back into doing its probing of the network, and that worked pretty well in my case. If you want to do a lot more time sensitive or faster applications, then maybe that's where you use something like C, C++ to have more control over the actual timing. For the way I was using that, this worked well, and MicroPython made it really easy to write the code.